And my brothers would be like,
yeah.
goldfish, and my mom's like,
shaving cream.
that has been here since before we were, so don't eat that.
I was so
I was sitting on that, I was like,
sometimes you get like a different reaction from what I usually like. Oh, that's cool.
this one.
23rd. No, 24th. 24th.
Oh my god.
Yeah, it's crazy.
Wow.
Yeah, I was excited. Yesterday was 123.24. 23 plus 1. I don't know.
Oh yeah. No,
It's
but
nice.
this way you got it
I wasn't super excited.
But it was easy to remember.
It was, yes, it was noteworthy. All right, my friends, let's all stop eating dirt. That's a good one on camera. All right, awesome. Let's just take a minute to come in here. So I ask that you please stop doing whatever it is you are doing. Stop producing. What's wrong with you, you crazy capitalist? Let's just sit for a second. What I'd like you to do today is just see what happens when you sit here without judgment. Where does your mind go? Ask you this question. Are you writing the thoughts or are you watching the thoughts? And then I ask you one final question. Who's watching? As we come back into our classroom, just take note of your breath. Wherever you notice it, maybe your nose, maybe your belly, maybe your chest. Let's come back, get some stuff going. Now we can produce products again, thank God. All right, my friends, so I want to start off with that after I see if there's any questions for you. Do you have anything you'd like to talk about? I know Luke has a question. And if you have the homework, just make sure to get it to me today. And I think I said I'd take them up till Friday anyway, so you can drop it by my office. I will be in there on Friday at 2 to 3. Is there anything you'd like to talk about? Luke, what's your question? Let's get rolling with that.
Yeah, so I was working on the second one.
Yeah, cool, awesome.
So one of them's about proving that these two triangles are similar. And it gives us Z and W in the in Euler form with the E instead of in like a rectangular form. Is it fine? So I was finding it, and I got it so that I didn't have to use the REI theta, and I could just leave it as Z. Is that acceptable for that? And then if I just show that two of the angles, two sets of two angles are similar for that, that's all I need. Right?
Yeah, so let's actually address that. What problem, I'm sorry, can you just help me? Which one?
Yeah, it's number 4 in section 3.
Ah, got it. Yeah. So we want to prove, we've got these two triangles, and this, I'm glad you asked, because I wanted someone to ask about this. We've got these two triangles in the plane. The first one is pretty nice, a little bit skewed like that. And we know that that's the complex number Z, that's a 1. And then here, of course, is 0. And they both share that 0, but the other one looks like an essentially scaled and rotated version of that first one. And then we have a U and a W. Cool. So they are asking us to show that the triangle 0, 1, Z. So that's 0, 1, Z. That's this triangle is similar to 0, W, U, or 0, U, W. So let's talk, what are the ways to show triangles are similar? What does it mean for triangles to be similar? Let's start there. Can somebody help me out? Help us all out. What does it mean to say two triangles are similar?
They're proportional?
Yeah, proportional. Basically, one's a scaled version of the other and maybe rotated, or maybe even flipped. But essentially, one is just a scaled version of the other. That's very nice. What are the ways to show that two triangles are similar? Christian, yes?
You could show that it's got like two proportional sides with like equal angle in the middle of both sides.
Nice. So side, angle, side. Did you all learn that? Yeah, the rhyme is starting to come back, right? It's almost like Sokotoa. Thank you, Christian. What's another one?
Angle, side.
Angle, angle, side. We need three things. Can you just do two sides? No, because, right, you could have that versus that. These could be the same length. You need to have that angle. So that's why you need side, angle, side. What else? Angle, angle, angle. Love it. And then the last one is side, side, side. So those are the ways. And I had this geometry teacher in high school who she was horrible. She was a horrible person. Like she was just like sometimes the people that teach high school are such mean, twisted bastards that you're just like, what are you doing here? Why are you helping young people or not helping them, as the case may be? Yeah, it was one of those classes we did a proof. Did I tell you this story already about her calling me a parasite? I think I told someone about it. Right? Right? So yeah, I just like didn't have to really do the homework to know what was going on because it just like the stuff came to me and yeah, she called me like a parasite for the whole class because I didn't do my homework, but I could do the proofs and stuff, you know. And it's like, what a sick whatever you are. And she was a cheerleading coach. She was also the cheerleading coach. So she had this little thing. She was very cutesy. She thought she was so clever. I'll settle down. It's a lot of scars coming up from high school. But she side, angle, side, angle, angle, side. And she had this stupid cheer, and that shit is scarred in my head. So, Lou, you asked a different question. You didn't ask about any of that. Yeah. Yeah.
So I guess then,
I mean, there must be other information here. Right?
yeah.
Yes.
I guess I just meant like, is it fine to leave it? Because above it, it gives you like the identity that you can take the argument of like, right, for example, you can do like U minus W over 0 minus W, and that's the angle of W.
Yeah.
Right?
Yeah.
So is it like fine to just leave it as like argument of whatever that's gonna be equivalent to? And then say that that's like equal to another one. Like, when I simplified it out, I got two of them that like, it's the argument of the same thing, so I can just leave it like that then.
I think I'm following what, let me get. caught
Sorry,
up
I just
here.
don't wanna give away the answer.
No, I appreciate that. I appreciate you. So we've got Z times W here. Let's take a look. So, I mean, one way to do it is just show that you can take this thing and scale it by a certain factor and get all these same lengths, right? So that's the
Yeah.
side. That's one way to do it. The one thing I would do is first crank out what Z times W is in that polar form, and I think it might be easier than what you're trying to do.
Yeah.
Let's take a look. So let's just get started here. Z times W, we're gonna multiply the arguments. And we're gonna multiply the moduli and add the arguments. So theta plus alpha. And then I can start labeling this diagram just based on that. And that's where I would begin with this, and I'm pretty sure that's where I did begin with this, is that this angle here must be theta to have that form, and this is R. And then this angle here must be alpha, and this length must be S. And then this must be, I wish I had multiple colors here, but that is theta plus alpha. And let's see, from that, can I actually figure out this little corner angle here? Can I do that? Let's see, because that's, yeah. So I think to label it like this, you can figure your angles out pretty easily. Is that helping you, Lou?
Yeah.
Okay, thank you. Is there anybody want me to say more about this? Just like Lou, I don't want to take away the fun of this all, but you could, there's a lot of different ways to proceed here. And I think probably all of those are viable options over there. Anything else you'd like to talk about? I can't say too much because honestly saying just a little bit more, like we were in DiffyQ, we were talking about unstable equilibriums, and the solution to this one is unstable. If I tell too much, it's all over. Good. Any other problems you want to talk about? Did anybody make any progress on this one? Where we had to show that theta was a right angle? Are you smiling because you totally did? No, I know. Okay, let's do this one together. Because there's some techniques in here that I want to talk about, and there's an observation in here that I made after a lot of suffering. But it's an observation that will help us along the way, and I think it's an important thing to share. So when I worked this problem the first time, there you are. I mean, first principles are we're going to use this result that we had last time. And that is if I have C0, C1, C2. Oh, and I'm glad everybody's here still, because I know the drop day was Monday, and I didn't know how you're feeling about it. I'm so glad you're all still here. It's quite a lovely thing. So that angle theta there is the argument of Z2 minus Z1 naught over Z1 minus Z. And that's the way to proceed here. Literally, this is the unit circle. 1, minus 1 are fixed points that we know about, and we know that Z naught lives on the unit circle. So what form must Z naught have in polar form? What does it look like in polar form? Remember, so I'm thinking R, E to the I theta. What do I know R is? 1, right? Because I'm on the unit circle. So this distance here, this is 0 in the center, that's just 1. Everything on that circle has modulus 1. So we've got 1. I don't know what, and I shouldn't say theta here, I should say phi or something like that. Because I don't know what it is. This would be the phi I'm talking about. But that Z naught has that form. It's literally e to I times some number, and I don't know what that number is. But that's observation one that's gonna help us go. And then we're gonna plug it in with this because this is gonna be Z naught. This is gonna be, one of these two is Z1 and the other Z2. And I honestly don't know which way to do it best, but we'll just do this. See what happens and then play with it. And do algebra and then hope for a great insight. Which was the part that bless you, yeah. That put the part that was the pain, but then I felt so happy afterwards. So that theta is going to equal the argument of, I already wish I had done it differently, but it's whatever. A Z minus, so Z2 is -1, and then minus e to the I phi over Z1 minus e to the I phi. And there's definitely some stuff that will happen along the way that you'll need to use in the future, for sure. So, I have to figure out that angle, and that looks pretty rough right now. But when we have two complex numbers in, quote, in ratio like that, what's the steps for simplifying that? What's the first thing I would do with this? Besides convert to polar form, what's the way to divide two complex numbers?
Multiply by the conjugate.
Multiply by the conjugate of W. Yeah. So that's gonna be what I do here. I'm gonna multiply by the conjugate of the denominator. So let's write that all out. Let's do some scratch. I'm just gonna play with this quantity for a little while. And so I'm gonna multiply by the conjugate of the bottom. Let's write this all out slowly and carefully together. So put that bar over the whole top, and then on top I've got this. And let's think about what that conjugate would look like for a second. Let's actually write that out in cosine plus I sine form. So let's consider this. So this is scratch, scratch. We've got 1 minus e to the I phi bar. That is 1 minus cosine of phi plus I sine of phi. Remember, this is just shorthand for that expression there, bar. Is that cool, Christian? Question?
No, you're good.
Yes?
Why are we multiplying by the -1 minus e I phi?
Thank you, because I did not, because I put the bar as a negative. Thank you. That's a beautiful observation. We shouldn't be. That's the answer. Is this, and now we're cool. All right, so let's simplify this out. This is actually 1 minus cos phi. That's the new real part. Just combining those two. And then I've got minus I sine of phi. So watch this little maneuver. What happens if I replace cosine of phi with cosine of minus phi? Have I changed anything? Is this the same as that? Yeah. It is. Cosine's an even function. So cosine of pi is cosine of minus pi, right? So here I'm using the fact since cosine of x is cosine of minus x, cosine is even in other words. I can do that. And then sine is an odd function. So over here, I'm gonna say since sine of minus sine of x equals sine of minus x, in other words, sine is odd, I can pull that minus into there. So this is equal to plus I sine of minus phi. Let me stop. Check that out. Kind of do it in a weird way. Starting to think I could have done this in a more clear way, but here we are. So all I did was move that minus inside here, and here I just replaced phi with minus phi because I'm looking to make those arguments look the same there, the thing that I'm taking the sine and cosine of. So that's a weird move, and you might not, I would imagine most folks wouldn't do that. So this is actually, now watch, I'm gonna do a rewrite here. This is, I'm gonna regroup. This is, whoa, hold on. I wanna do this in the clearest way possible because I know where I wanna go. Okay, I think we're gonna be all right. So this is, why did I do it this way? I wonder if they can hear me talking to myself. So this is 1 minus cosine of minus phi plus I sine of minus phi. Son of a. Yeah, I'm sorry. This is stupid. But this is all legit, but I don't think it's going to be very obvious what's about to happen. Let me just show you a different result and use that more directly. So apologies. More directly. That word's directly. The conjugate of e to the ix is the conjugate, this is what I'm trying to get at. I sine of x conjugate, that is equal to cosine of x minus sine of x. That's the definition of conjugate. And now I'm going to rewrite this as cosine of minus x plus I sine of minus x, using the same stuff, using these two things that I just used before. So let me stop here. Does this make sense? Yes, okay, cool, all right. I could tell this wasn't going good, so we'll just back out, right? Pretend like it never happened. There we go. So I'll come back to that in a minute, just get rid of that crap. And so this is actually e to the minus x I, just by the definition of e to the ix, right? It's here, I'm just replacing the x with minus x. So in other words, what I'm saying is this. To take the conjugate of that thing, you just negate the exponent. That's what I want to say. So this is a good rule to write out and keep in mind this semester, that this is an identity. That'll help. Sorry about that. Apologies for that confusion that may have caused. But it sure makes this easy. Let's get a couple other conjugate properties out here that will be helpful. Conjugate properties. So first off, z times w conjugate is the product of conjugates. Z over w conjugate is the quotient of the conjugate, so it's almost like it distributes. The operation does. And is that the one? I think that might be good. Oh, yeah, and one more. Z plus or minus the w conjugate is the plus or the sum or the difference of the conjugates. So conjugation acts really nice. It just moves like you would want it to. Nothing weird happens. So these three properties are going to help me move forward. That means now I can do this with much more intelligence and clarity. So I'm gonna just rewrite this part here using those properties, including that one. So this top, I'm just copying this part over. Like so. So that's just copied. And now I'm gonna use the difference, the conjugate of the difference is the difference of the conjugates. I'm gonna write that there, and we're gonna get rid of it real quick. So I'm just spreading that conjugate love all around. What is the conjugate of 1? 1, yeah. Remember, think about the geometric interpretation of conjugate. It's just flipping over the x-axis. And if you're on the x-axis, you don't move. So the conjugate of a real number is just that number. So this just becomes 1 minus e to the, now I'm going to use that property, minus I phi over 1 minus e to the minus I phi. Oh, and copy this stuff here too. So I think we made a little space. So this just copies in here. Just copy that. Get tiny 1 minus e to the I phi. And here, this piece is just this thing that I've written here. And so let me rewrite all that because that looks pretty atrocious. So I've got on top minus 1 minus e to the I phi times 1 minus e to the minus I phi. And on the bottom, and I'm putting them in parentheses because we're going to FOIL, 1 minus e to the I phi times 1 minus e to the minus I phi. Yay. Okay. Yeah, pictures are worth a lot. And hey, apologies about the video from Monday. I had a snafu and it's still uploading. Sometimes the YouTube stuff gets weird. So 24 to 36 hours is what it can take sometimes. But it will be up soon, as will this one. So now, FOIL. Bless you.
Thank you.
Hey, could you do the FOIL, please? So I can eat jelly beans. Oh, I better not eat that warhead. Sanity check is available. And let me know if there's any questions about any of the pieces. The ones on the L came because when you add these exponents, you just get e to the 0. So that turns into a 1. That times that is just 1.
Why do you get 1?
Cool. So for the L part, so I've got, let's forget about the minuses, because minus times minus will give us a plus. But then I've got this L. E to the I phi times e to the minus I phi, and that's just add the exponents, and so I get 1. Does that sound good?
Yes.
Awesome. Other questions? No. You good? Yeah, cool. Neat stuff happens here, cancels. So we're just gonna get e to the minus I phi minus e to the I phi over, and then in the bottom I'm gonna have 2 minus e to the I phi, and I'm gonna actually put that part in parentheses for a second. So I'm gonna have 2 minus e to the minus I phi plus e to the I phi. So check that out. And now I would like you to have the fun here. So now we're almost to the place where we can say that this is a 90-degree angle. Turn this into cosine plus I sine form. So replace with cosine plus I sine form. Go back to it. I would never carry around that cos plus I sine form, but I would write this and then come back to it. It's going to help right now. Go forth in cosine plus I sine, please. Pretty things will happen. See if anything cancels. See if anything combines. Use the properties of cosine is even, sine is odd. when needed. Let's just all arrive here. We're not going to leave anybody behind. you're already here, you might start wondering how this proves our result. You might start wondering two things. One, how do we know the bottom isn't zero? And two, how does this get us to the place we want? Because we're there. And I'll give an even more suggestive rewrite. It was that rewrite that got me, that stopped my insanity and the ache inside. Can I help anybody with the algebra? Because this insight, like it's seriously, it's, once you hear it, you will not forget it. But it's a hard leap to make, it's weird. Remember what we're trying to do is, what is the argument of that output? We wanted the angle of that thing. And the angle of that thing will give us this angle right here. That, the angle of that is literally this angle, because that's how we started. So let's start with some, just making sure we're algebraically cool, and I'm happy to clarify any steps. Are we all getting there algebraically? If not, where can I go? It's this step. Which, is this good? Is this one good from here to here? Like a doctor, like tapping on your knees. So if we can get to here, that's good. Notice that this bottom has this denominator, this 2 minus 2 cosine phi. So I just want to make sure that that's not division by 0. But if you look at the graph of the bottom, if this is phi and this is 2 minus 2 cosine of phi, the graph looks like this. You can see that that angle, or that quantity is only 0 when phi is 0, and phi is the angle for that point up there. We wouldn't have a triangle if that angle was 0. So we're assuming it's positive, and we're assuming that it's not a full revolution around. So the fact is that this quantity is positive if phi is between 0 and 2 pi. So we're totally cool on not dividing by 0. Why does that prove my result? What is the argument of that number? Where does that number live in the complex plane? Roughly.
The top half.
Top half, or maybe the bottom half, right? Is one of the two. Because that's a pure imaginary number. This is a real quantity. So this is just a real number times I. That's a real quantity. So it's either here or it's here. What is the argument of a number that lives up here? 2? 90 degrees. What is an angle? What if it lives down here? What's the argument? Negative pi over 2. So it kind of just depends, and if we go left or right, that was the thing that blew my mind. I was like, holy shit, I think I might be starting to understand this stuff a little bit. So that is a pure real number, which must have an argument of plus or minus pi over 2. So this thing here has an argument of plus or minus pi over 2. And we're done. That's pretty heavy. But it isn't also, right? It was literally starting with the definition of this angle and just keeping our wits about us, staying calm, cranking through, but then making that big weird leap at the end. That big leap will come up with another bonus problem I will give you later this semester, one that took me weeks without this observation. With this, things get better. All right, you've seen enough of that, but we're not done. We're just beginning. Let's do more stuff together, my friends. Is there any questions over this? Everybody seems pretty fried. If you've been sitting here with me since 12:30, you're probably pretty toasted. Ella, yes, my friend, thank you.
Can you re-explain how we got from, like, I understand that the part in the brackets, like the -2 sign,
This part here,
like
yeah.
all that's a real number, but how did we get from there to knowing it's pi over 2?
Cool, awesome, so let me explain that. Thank you for asking. So you're cool with this, getting up to here, right?
Yeah.
So remember what that was. That computation was basically the angle between this line and this line. Is that, you're with me on that, right? So this was the angle betwixt Z1 minus Z naught and Z2 minus Z naught. So we cranked it through, we got the coordinates for this. This was just e to the I phi. We don't know what phi is, doesn't matter. And I found that using the formula. So I got to here, kept cranking, came down, blah, blah, blah. Got to here, and you're all cool with that, so that's great. So this is just some real number, this part. I don't know what it is. It's a crazy real number, but it's some real number. So that quantity simplifies to a real number times I. What was I trying to find? I wanted the angle of this thing. I wanted the arg of this, the argument. So I cranked out this quantity, and now I'm asking, okay, well, this quantity looks like this, looks like this, looks like this. So up here, this is equal to the argument of some real thing times I, some multiple of I. And then I come back, oh, it's like, okay, cool. All I have to do is know what is the argument of a pure real number, a pure imaginary number. And so it's either up here, if that real number is positive, or it's down here. What is this angle? 90 degrees.
Okay.
Does that make sense now? Thank you for asking. Cool. Now it's kind of crazy, right? Yeah. You weren't the only one who probably needed to hear that, so thank you. Truly appreciate it. All right. I was gonna have, let's see what kind of time we have. Theoretically, there's a quiz next Monday. I put it up on World Class. I don't know if you saw that, like in the, I think I put it in the calendar. The quiz is pretty straightforward, and all the details are there. I don't know, if we don't get there by the end of class today, I'll just move it to the start of class on Wednesday. Does this sound okay? Yeah. So I put up a couple, one of them is just know by heart the blurb on page page 30. There's this little gray box. Know that. And I've got that all written out in the calendar item. know that by heart, that item. Because this will be a closed notes quiz, and I'm just asking you to learn that and remember those definitions. If you're unsure how to remember definition, or not quite sure how the best way to learn it, talk to me and I'll help you with how I learn definitions. Happy to help with that. And then I'm gonna give you a quadratic equation to solve. That sounds easy. There's some stuff involved. But let's talk. Let's see if we can get there. Let's see where we can get today. And if not, we'll move it to the start of class on Wednesday, or the end of class, actually. Because I want you to have time. I want you to have plenty of time, and I want to be able to talk about it together before throwing you to the math wolves. Cool. So today, we're going to talk about lines and circles. In the complex plane, C, that big old C, complex plane. So let's start. We're in the plane. We have this X and this Y, and this is the real part, this is the imaginary part. And everything in here looks like that. So I have X and Y. That's my Z right there. If we weren't in the complex plane, what is the equation of a line? What is the general equation of a line in just good old XYville? Not thinking about this class. So before you came in here, you knew stuff. You might be wondering if you still know things. You do. What's the equation of a line in 2 dimensions? Just give me one form.
Y equals mx plus b.
Thank you. Y equals mx plus. So we know good old y equals mx plus b, and we put it in that form so we can grab the slope and the intercept, and that's a useful tool. More generally, we might get something like this, right? Get that, and you could take that, bless you, and you could turn it into that, and you could even write it the way our book does, like that. You could just move that C to the other side. That's the equation of a line. So let's turn that into an equation in Z. And then we'll see how our book gets our new equation for a line. So an equation in Z. All right, well, hey, check this out. If Z is x plus iy, and Z conjugate is x minus iy, I can recover x and y in terms of Z by solving this thing for x and solving this thing for y. So check this out. Add down. Oh my God, look at that. The conjugate makes the things cancel, right? It's just the plus iy and the minus iy cancels. So in other words, the x is actually 1/2 z plus z conjugate. Cool. Let me stop. So if I gave you a complex number, Z, you could recover the real part. So this, notice that this is just the real part of Z. Let's do that again. Let's try to find Y. So again, and we're exclaiming because we haven't lost our energy despite it being the hour that it is. What would be a good way to cancel the x's out? So by adding, I killed off this part. How would I kill off the x's? What simple math operation? Subtract. Yeah, let's subtract. And then the x's look in. So I'm going to subtract. So here I plussed. Here I'm going to minus. And I'm going to get z minus z conjugate equals kill 2IY. It is overwhelming. It's intense. Yeah, it's like gets lumped up in your throat. So then y is 1 over 2I z minus z conjugate. And that's good. We'll just leave it at that. So those are cool. Those are useful. Those will be handy occasionally in here. I would make a little star by them or something. Useful relationships. So now let's go to this thing and just literally plug in our new formulas. So for x, I'm going to plug in this. For y, I'm going to plug in this. So this, using these two things, becomes the a times 1/2 c plus c conjugate plus b times 1 over 2I z minus c conjugate. I'm probably going to spare us some of the algebra, but I highly recommend you work it through on your own. Plus c equals 0. Let's see, where did that get us? So, working this all through and grouping together stuff that has z on it and stuff that has z conjugate. So after some work, which I do recommend you do, because it's soothing work, we can get this into the following form. Minus a plus bi c plus minus a minus bi c conjugate minus 2c equals 0. After some work. Just simple algebra, nothing funky or weird. Just regrouping by z and z conjugate. And notice, wait, let me ask you, what is the relationship between this thing? If this is alpha, what is this? Complex wise, what do we call it?
Alpha conjugate.
Thank you, that's alpha conjugate. And then we're just gonna call this dude right here, this whole thing, we're gonna call that beta. So the equation of a line in the complex plane looks like this. And that's new to everyone. That's new to me. That was new to me. That looks weird. But the only way to see that it's truly our good old friend, ax plus by plus c, is to do this work here and get that. Cool, so that's the equation of a line. That's one of the things I will ask you to give me. Let's talk about another way to define a line. So this is algebraically. Let's talk about geometrically. How do I define a line in the complex plane? What do you need to make a line in just normal, in the normal plane? What do you need? Two endpoints. Yeah, I need 2 points to get a line, right? So if I have 2 points, I can most definitely draw a line between them. Get that. But there's another way. In the complex plane, or even in the plane we can do this, it's just not as pretty. If I take 2 points, P1 and P2, and let's think about the line segment that joins them. Think about the perpendicular bisector of that line between the two of them. So in other words, the line that passes just like this between the two of them. Every point on this line, Z, is equidistant from those 2 points. No matter where I pick on there, no matter what Z I pick, it's going to be the same distance from those 2 points. So that's the second way we will define a line and think about it. And we will think about it this way. And we'll use that. And let me write that out. A line is created by taking all points Z equidistant. See, this is the geometric formulation. Equidistant from 2 points. From two points P1 and P2. It's the other way. Now, I'm not going to take the time to prove that, but it's in my notes. But I don't think you want to see it right now. It's a little late. I'm feeling a little punchy high.
What does it say after it is?
That's a good question. Created. Thank you. Created. It is the locus, to say it even more mathily and Greekly, and probably Latin-y. It is the locus of points equidistant from 2 other points. You can see how if you just rotate these a little, the line tilts. Are these 2 points unique? So I've got this line L. Is that the only 2 points that create L in this way? Right? No. In fact, any other 2 on this line. Oh yeah, that's right. You guys split early. Yep. Bye. Thank you. Any other 2 points, if I just move out the same distance, they can work as well. So those points are unique for a particular line. Just a thing to note. I would highly recommend you look at the result and maybe just work it through or follow it through on page, it's theorem 242. So this is theorem 242. Take the time to just read through the proof of that and reinforce some of the stuff that we have done today. It'll be good for you. That's good medicine. And I'm happy to talk about it. All right, let's do circle and then let's solve a quadratic and call it a day. Circle's easy. I don't have to get too fancy with that. So, fun fact. If, I'm going to get a little mathier here, if Z1 and Z2 are complex numbers, you might not have seen this notation before, or it might have been a while. This just means element of or in this set C. So this just means Z1 and Z2 are complex numbers. That's all that means, just math, beautiful math notation. The modulus of Z1 minus Z2 is equal to the distance between Z1 and Z2. So if you want to find the distance between 2 points, you just take their difference, literally subtract them, and then find that modulus of that. So, if I take a look at the set of all Z such that Z minus some fixed point, so the Z is variable. Now I'm looking for all the Z so that Z minus Z naught, the distance between Z and Z naught, let me write that, is a constant, R. I have a circle of radius R centered at Z naught. So this describes a circle of radius R centered at Z naught. Cool. We're actually going to get, I think we're actually going to get to do a quadratic here. I think. I start like gradually peeling ahead to what is gonna come, we'll see how it goes. Let's make I've already said, let's make this quiz on Wednesday. So that I don't have to cram this stuff in the last 15 minutes. Does that sound okay? So you have time to process. I have time to not just be insane. But I will do this all here. So let's just talk about square roots in the complex plane. Suppose Z naught is a complex number, so that's Z sub 0 is a complex number. And I'm going to draw it out. Here's Z naught, I'm going to put it into polar form, R theta. Nothing amazing has happened yet. I'm just setting this up, getting ready to tee off here. We want to solve Z squared equals Z naught. So I want to find the thing that I square to get that number. So I'm going to convert the whole dang thing into polar coordinates. So let's assume Z is rho e to the I phi. And I'm going to find rho and I'm going to find phi. But this makes it so easy. So let's plug that in. So rewrite. Let's call this star. Rewrite star. And it becomes rho e I phi squared equals, and now I'm going to put my form of this thing in. It's r e to the I theta. Should label that over here. What do you do with these exponents here? Well, what can I do? How can I rewrite this whole left side? Somebody help me out.
Can you do p squared e to the 2 I phi?
Yeah, so it's rho squared. Or p, whatever, p's cool too. Yeah, it's all good. E to the 2 I phi. Oh. Does that make sense? Properties of exponents and stuff. Okay, good, we know those, awesome. I know it's been a long day. So remember, this is the direction part, and these are the moduli. So it must be true that rho squared equals r. And it must be true that this angle here is equal to theta, but it could involve some rotation around. So this k is a whole number, so k is an integer. Because if you add 2 pi to that argument, it just gets you back to the same place. So some things are good here. Now we know that we're always going to assume our modulus a positive number. So this one here says that the modulus is just the square root of the original modulus. So that's cool. Let's just star that off because we're done.
I have a question.
Yes, thank you.
Why did we carry the I down on the side of phi and not on the side of theta?
Thank you, because I shouldn't have. Thank you, good one, Kidra. Thank you. Yeah, thank you. And if I had, I would have canceled them right away, so thank you, Brendan. Yeah, appreciate you. Good stuff. So now phi is just half of theta plus some multiple of pi. And there's only So the multiples of pi are gonna flip us. If we just take k equals 1, that gets us 180 degrees. If k is 2, that gets us back to where we need to be. So there's only 2 angles to worry about here. So phi equals just theta over 2, or it equals theta over 2 plus pi, the one exactly on the other side of the origin. So we're almost done. Definitely glad I moved that quiz. Definitely glad. So let's summarize. Mostly. So the square root of z naught is 2 numbers. And you're used to this, used to a plus root and a minus root in general. But in the complex plane, this kind of represents 2 numbers, essentially. It represents one and then the other one on the other side. So it is 2 numbers. And the first number, if z naught equals re to the I theta, then the square root of z naught is square root of r, e to the I theta over 2. So just cut the angle in half and take the square root of the modulus. And the other option is square root of r, e to the I theta over 2 plus pi. And I'm going to tweak that. Notice that that is square root of r, e to the I theta over 2, e to the I pi. I'm just using properties of exponents here. What is e to the I pi? That's a pretty one. What's e to the I pi? -1, quite deal, yes, yes. Right, and how do we know that? Well, we just go around the unit circle, pi degrees, and that gets us right at -1. That made me happy, thank you, Olivia. So, that's just -1. So the other one is the one you'd expect. So here's your answers. It's either this or it's this. So let's just take a quick square root and be done with it for today. One of the funnest things to write. Like what? Right? What? You gotta be kidding me. Step 1, write I in polar form. It's straight up. Go up 1 unit. So the square root of I is equal to the square root of 1, which is 1. E to the pi over 4i. I just cut the angle in half, take the square root of the modulus. Or it's the opposite of that. Now I just gotta find e to the pi over 4i, and I'm done. And so let's do that really quickly. So this is, let's just write that out. It's just e to the pi over 4i, or negative e to the pi over 4i. So to find e to the pi over 4i, I just sweep up 45 degrees. And then just find the cosine of pi over 4 and the sine of pi over 4. Some of you probably know this stuff. What is the cosine of pi over 4? Don't we have some unit circle folk out there? You're like,
2 pi over 2.
oh, square root of 2, thinking in the wrong direction. Square, it's okay, it's all good. Square root of 2 over 2, that turns out to also be sine of pi over 4. Square root of 2 over 2. So, the square roots of I are equal to, so I'm just going to convert that. square root of 2 over 2 plus square root of 2 over 2i, or square root of 2 over 2 minus all that. And so here's one of them, right here. And the other one's directly across, right over here. Yikes. So, I would recommend trying to start the homework. Don't solve the quadratic, or just start looking at the quiz stuff. Maybe I'll give you one extra problem here to do. Oh no, I think I've got some good practice problems in the, yeah, look at the quiz prep, but the quiz is until Wednesday, so no stress. Thank you, friends. Appreciate you. No, no.